listen-only mode.
Okay, hello, welcome. This is Tom Kite, also known as the Tom behind asktom.oracle.com. For about the next hour, I'll be talking about getting the right cardinality, or in other words, how to get the right query plan. The first question I'd like to ask anybody out there is, why do we gather statistics? Frequently answers I hear to this would be things like, oh, so the optimizer can find the right plan. That's sort of it, but that's too vague. Or to give the optimizer more information about the data. That's another part of it, but still a little bit too vague, too broad. In short, there's a one-word answer to why do we gather statistics, and that one word is simply cardinality. It's so that the cost-based optimizer can accurately compute an estimated cardinality for some step, some part of a query plan, and then based on that, start to do things like assign costs to that step in the query plan and aggregate costs for all of the subsequent steps in the query plan. This estimated cardinality, the ability of the optimizer to get this estimated cardinality is really important. Can't be stressed enough. I have two sayings. One of them is wrong plan means the optimizer gets the incorrect cardinality. So for example, if I gave you a simple query, select star from table where x equals 5, and I gave you statistics like the table in question has 1,000,000 rows in it, the column x has 10 distinct values inside of it, and there is an index on x. And this is all the information you have. If you were the cost-based optimizer, you would probably do something like take the number 1,000,000, the number of rows in the table, the number of distinct values in column x, which is 10, divide 10 into 1,000,000, come up with 100,000, and say, I think this query is going to return about 100,000 rows. Now, if I was to get 100,000 rows out of a table, and those rows were spread throughout the table itself, they weren't concentrated in one location, I would probably use a full scan. So I, as the optimizer, estimating 100,000 rows, will come up with a full scan plan. But what happens if you run that query and where x equals 5 ends up getting 5 records instead of 100,000? There, because we had the wrong estimated cardinality, we came up with the wrong query plan. If we would have been able to guess 5 rows instead of 100,000, we would have come up with the right plan. Another way of putting this is, if you have the wrong cardinality, odds are you have the wrong query plan. We estimated 100,000 rows. We came up with a full scan. We actually run the query. It only gets 5 records. So in real life, how would you fix that particular issue? Well, apparently, the values in column X, there's 10 unique values, 1,000,000 rows in the table, are not evenly distributed. X equals 5 only has 5 values. That must mean that some other X equals value has way more than 100,000 values. So if we were to have gathered histograms, additional statistics, the optimizer would have been able to come up with a more optimal query plan. It would have gotten the right cardinality estimate and the right plan. So this is just the tip of the iceberg, that this estimated cardinality is really important. Here's another quick and dirty example I use a lot. I've created a table. It has 2 important columns in it, flag 1 and flag 2. These 2 columns only have 2 values, yes and no. But notice how when I created the data at the top of the screen, if flag 1 had a value of n, flag 2 apparently has a value of y, and vice versa. If flag 1 is y, then flag 2 is n. That means that there apparently are no rows in this table right now where flag 1 equals flag 2 equals n or equals y. They're all yn or ny. Now, we go ahead and create an index on those 2 columns, and some people might look at that index and say, that's a really bad index. Flag 1 and flag 2 only have 2 values, not very selective. I look at that index and say, that index is very selective. If I'm trying to find all the rows in the table where flag 1 equals flag 2, that index could be very useful. In fact, that index could be used to find no rows in the table much faster than a full scan to find no rows in that table. So that index actually does make sense. We go ahead and gather statistics. These are just basic statistics at this point. And if we were to ask the optimizer a couple of questions, this is its thought process. This is how it would estimate the cardinalities. If we were to ask the optimizer, how many rows are in table T? Select star from T, it would have a really easy job. It would just go to num rows in user tables, and it would be able to figure out the estimated cardinality pretty much accurately. If we were to ask it, select star from T where flag 1 equals N, it would be able to come up with a good estimated cardinality for that, because in the previous slide, when I gathered statistics, I asked it to gather histograms explicitly on those index columns. So right now, the optimizer knows that flag 1 only has two values, N and Y, and that half of them are N and half of them are Y. Same with flag 2. It understands that perfectly as well, and will come up with a very good estimated cardinality for that. However, when I ask it the last question there, select star from T where flag 1 equals N and flag 2 equals N, this is where the optimizer is going to have a hard time, given the information it has. This is where you would have a hard time coming up with an estimated cardinality, given the information you have. If all you knew were the number of rows in the table, the high value and the low value for flag 1 and flag 2, and you had a histogram for flag 1, and a separate histogram for flag 2 that would tell you exactly how many rows were flag 1 equals N and flag 2 equals N, you still would not be able to come up with a good cardinality estimate for flag 1 equals N and flag 2 equals N simultaneously. You don't have any information on those two columns together. You only have information on flag 1 and then elsewhere on flag 2. What the optimizer's done here is it's guessed. It took the probability of the part of the where clause where flag 1 equals N, which was 1/2, and it multiplied it by the probability of the other part of the where clause, flag 2 equals N. It just used really basic statistical methods. It said if the probability of P1 is 50% and the probability of P2 is 50%, then the probability of P1 and P2 is 50% times 50%, or 1/4. It's going to estimate 18,000 records. And in fact, if we run through and we look at some plans for these queries, we can see this in action. I ask it to show me the plan for where flag 1 equals N. It says, oh, I'm going to get about half of the rows, 36,000. Where flag 2 equals N, I'm going to get about half of the rows, about 36,000. Where flag 1 equals N and flag 2 equals N, I'm going to get 18,000 rows. This is wrong. We know this is wrong. It's going to get 0 rows. A full scan would be a really slow way to find 0 rows in the table. This should have been an index range scan. Why isn't it? Because the estimated cardinality is so far off. The estimated cardinality should be down in the single-digit range. Here, it's off by many orders of magnitude. And when we get estimated cardinalities that are off from the actual cardinalities by orders of magnitude, that's when we get the wrong query plan. So how do we diagnose this? How do we figure out where it's going wrong? A real simple way is to use this hint, which is not really a hint. This gather plan statistics, when used in the query, will create a query plan that has additional instrumentation in it. That hint doesn't affect the execution plan, doesn't affect what the query gets compiled into. It just affects how much additional instrumentation information, how many IOs I did, how many buffer gets, how many this, that, and the others, what CPU I used, what my actual cardinalities were versus my estimates, and so on. So we go ahead and run that query. We get no rows selected from it. And now we can use DBMS Xplan to display that information that was instrumented into the query for us. And so here I'm using display cursor on the last query executed in my session, using the options all stat last. This gives me the actual query plan that was used. So this is not an explain plan. This is coming from the $SQL information. But it's also showing me for the last execution of this query what the estimated rows were, 18,181, versus the actual rows, 0 in this case. when you have a query that you think has a poorly performing query plan, this sort of approach should be your first step. Get the estimated cardinalities, compare them to the actual. You can get the estimates by doing an explain plan, for example, and an actual by looking at a TK Prof report. You can get the estimated and the actuals using the approach I just did here. You can see the actuals versus the estimates in the real-time SQL monitor in Enterprise Manager if you have access to that. But what you're looking for is the estimated rows to diverge from the actual rows by orders of magnitude. And here we have that case. And if we look at the where clause, we can start to think about why. We can see the filter down there. That filter is what drove that estimated cardinality. Why would the optimizer get that wrong? Oh, because it knows nothing about flag 1 and flag 2 simultaneously, just has stats on each of those columns. So what are some of the things we can do? Depends on the release, depends on your knowledge of Oracle. One of the approaches we could take is a capability that was added in Oracle 9i, dynamic sampling. Dynamic sampling is traditionally used to fill in missing statistics. Well, I'm running a query against a table that has no stats. The cost-based optimizer needs stats, so I'll gather some statistics while I'm hard parsing that query for that table that's not analyzed. That's the default level of dynamic sampling. We can turn dynamic sampling up, and in this case I turned it up to level 3. The default is level 2 currently. If I turn it up to level 3, dynamic sampling will do everything it did at level 2, plus if it ever had to guess at a single table predicate, it's going to go back and validate that guess. So in this case, it looked at its where clause and said, I guessed at the estimated cardinality for that access of flag 1 equals n and flag 2 equals n. I'm going to validate that guess. And what it did was, when it hard parsed, it ran this sample query. Now the sample query ran very quickly. It hit very little of the table. It happened only during the hard parse, so if I was to execute this query over and over again, this sample query wouldn't have to take place. But as you look at the where clause, you can see it's looking at flag 1 and flag 2 and trying to understand if there's a relationship between these two columns. And because we allowed the optimizer to run this query to validate its guess, when it actually optimized the query on the previous slide, we can see the estimated cardinality went from 18,181 down to an estimated cardinality of 6. And because it got an estimated cardinality of 6, it shows a scan, and that was the right query plan. Now note, it did not estimate 0. I mean, 0 is the actual number of rows. The cost-based optimizer will never estimate 0 for an estimated cardinality. It will always estimate at least 1. And what I said before was, it's when the estimated cardinalities get to be off of the actual cardinalities by orders of magnitude that the query plans go bad. In this case, 6 is more than close enough to 0 to get the right query plan. The estimate doesn't have to be exact, doesn't have to be perfect. It just has to be closer than close enough. So in this case, by running the sampling query, we got what we needed. Now, the cost-based optimizer is just a mathematical model. So I'm going to show you another example that even if you get the estimated cardinalities really close, you still might run into some issues. Okay, so I'm going to create a table as a 1-character column string, and then it has all the other columns of all objects. I create an index on that 1-character column and the object name and gather stats on this. Now today, the optimizer gets a query, select count of sub-object name from table where string equals t. Because the cost-based optimizer estimated 292 records coming out of this table, it decided I'm going to use an index range scan, table accessed by index row ID. Now later that night, somebody comes along and gathers statistics. During the day, people have done inserts, updates, deletes. They change the information in the table. But the DBA comes and gathers statistics that night. The very next day, instead of an index range scan, that query will have a full table scan. There is some point where when an estimated cardinality just increases by 1, or decreases by 1, your query plan is going to change. You all probably knew that in your head, but unless you actually look for it, you don't see it very often. What you do see every now and then is a query plan that used to be good yesterday, gathered stats, and then tomorrow it doesn't run as good. And the reasoning could be partially due to this. There's these tipping points. You know, if 292 rows was good to get out of the table via an index yesterday, getting 293 rows via the index today is probably okay too. Probably getting 294 rows is going to be okay using the index. But at some point, there is an actual number that, hey, the full scan is better than the index range scan, even if it's just a little teeny tiny bit better. At the end of this presentation, the very last section, I'm going to show you how to protect yourself from this 292 row using an index to 293 rows doing a full scan. Maybe it's not right to flip the query plan yet, and we'll take a look at a capability that exists inside the database to help protect yourself from these changes. But let's take a look at statistics and the importance or relevance of them as far as getting the right estimated cardinality. Things do change over time. I'm going to be speaking predominantly to Oracle Database 11G and above. And in 11G, you should, as often as possible, allow everything in your DBMS stats call to default, except for, obviously, the segment name if you're doing it table by table or index by index, and the degree of parallelism if you want to use parallel query during the stats gathering. Why is this? Because the algorithms for DBMS stats changed dramatically between version 10 and version 11, especially with regards to the method opt and the estimate percent parameter. Many people in the past used the estimate percent in an attempt to get statistics to gather faster. But the smaller they would set the estimate percent, potentially the worse the gathered statistics would be. So you could gather stats quickly but have bad statistics, or spend a long time gathering stats and get good statistics. And there was sort of this trade-off. Starting in version 11, you will find if you leave the estimate percent to default to an auto sample size, the statistics you get will be almost as good, if not better, than a full compute statistics in 10G and before was. And you will find that the auto sample size in 11G is going to be as fast as using a 10% or smaller sample was in 10G. Meaning, with the auto sample size in 11, you're going to get stats that are nearly perfect, and you're going to get them as fast as if you were using a sample in previous releases. I should point out, if you use estimate percent and set it to some number in 11G, you're actually using the old 10G algorithms to gather stats. Only by letting estimate percent default will you be able to take advantage of these new algorithms that can do things like incremental statistics gathering on partition tables, as well as get correct number distinct value computations and other vital statistics gathered correctly. So let those default. However, that said, there's something you should be aware of. If you let the method opt default, the types of statistics that are gathered may change over time. The optimizer, the runtime query execution engine, has been watching you since version 10G. Every time you run a query and it breaks the where clause apart, it's remembering what you've used in those where clauses and group bys and other operations. So for example, here I'm going to create a table where the first 499 rows have a status of 1, and the rest of the rows in the table have a status of 99. So this some status column has very skewed information in it. If I said some status equals 1, I'm going to get about 500 records. If I say some status equals 99, I'm going to get tens of thousands of records. Now we'll go ahead and gather stats from this table. And notice I've used all the defaults for method opt, estimate percent, and everything else like that. And we'll go ahead and take a look at the statistics that are available in the table, and we can see that currently there are no histograms. So basically, the only thing the optimizer knows is the number of rows in the table, number of blocks in the table, high value for some status, low value for some status, and maybe number of nulls. But it doesn't have a good, clear picture of the data values in some status. It knows the number of distinct values, knows there's 2 of them, but it doesn't know about the data skew. So we'll go ahead and create an index on this sum status column. This index makes sense because if I say sum status equals 1, using the index to get 500 rows is going to be smart. If I say sum status equals 99, using the index would be a bad idea. Okay, so this index is selective for some values of status. So we'll go ahead and run a query, select star from T where sum status equals 99. Now, we know this table has about 72,000 rows in it, but the optimizer right now is estimating I'm going to get half. I'm going to get 36,000. And in fact, if I said sum status equals 1, it will come up with the same exact cardinality estimate. And that's because the optimizer only knows that the table has 72,000 rows in it. There's 2 values for this specific column that we're using. The high value is 99, low value is 1, and that's it. If that's the only information you had, this is the guess you would come up with as well. So it's going to do a full scan for both values of status. So we'll go ahead and gather stats again. Now notice I didn't update any of the data. I didn't change anything. All I did was I ran this one query. When I ran this query, the database recorded into the data dictionary the fact that we use some status and a where clause. And in fact, we can now see that after gathering stats, there are histograms. There is a histogram on this sum status column. And the next time we go and ask the optimizer to optimize, it looks at the where clause, says, ooh, sum status equals 1. Let me go check out that histogram. It's about 500 records. I'm going to use an index range scan. Sum status equals 99. Ooh, that is a very popular value. The histogram says there's about 72,000 values for that. So I'm going to use a full scan. So now we're getting the right estimated cardinality, and we're getting the right query plan. One thing I'd like to point out is this query plan didn't really change for sum status equals 99. It was a full scan before, it's a full scan now. What did change, though, was the estimated cardinalities. In the first full scan, it thought it was going to get 36,000 records. Now it thinks it's going to get 71,000 records. Even though this particular query plan didn't change, having those histograms in place for that skewed bit of information is important because I might be using this query that you see on the screen now in other queries, in a join, in a subquery, as a filter sort of operation. So getting the right estimated cardinality for this where clause, even though it didn't change the query plan in this example, is still relevant. What did change, though, was the query plan for sum status equals 1 because we got the right cardinality estimate. So getting those right cardinality estimates is extremely vital. And one thing I'd like to point out with indexes, since Oracle 10G, anytime you create or rebuild an index, okay, and that index is on a non-empty segment, the index will automatically have statistics. So in many cases, you don't even have to gather statistics on your indexes. I'd like to also point out that in version 12, the current production releases of Oracle, the same is true for a direct path load into an empty table or a create table as select. So in version 12, that create table as select star from all objects would have automatically gathered statistics on the table as it was being created, and the create index would have gathered statistics on the index as it was being created, removing the need to gather those statistics. So let's take a quick look at some other ways to get statistics. There's DBMS stats to set statistics on table. If you know the statistics, just tell us. If you've just done a data load and you know you put 1,000,000 rows in there, you can just tell us you put 1,000,000 rows in there. The fastest way to get statistics on there might be just to set them. You can also copy statistics. If, for example, you have a partition table where every day you add a new empty partition and you end up filling it up by the end of the day, you're going to need to have some representative statistics on that partition when you start out in the morning. Because what you don't want to have happen is all of your query plans be developed for an empty partition, and then as that partition fills up over the day, that query plan becomes worse and worse and worse. What you would probably want to do is start with a query plan that was built as if the partition was full. Because when the partition is empty, most of the time, it doesn't matter what query plan you use against it. It's going to run okay. So what you might want to do is start with a query plan assuming that the partition is full. So what you can do is, as you create a new partition, copy the statistics from the last partition so that you start out with some representative statistics, something that looks like that partition will look like in the middle of the afternoon, for example. And then at the end of that day, you gather statistics on that partition, you create tomorrow's partition, and you copy those statistics over, and you keep doing that. This is what we do with AWR, the Automatic Workload Repository. Under the covers, we use partition tables to manage that information so we can purge it easily. But we also have this missing statistics problem as we add new partitions. So every window of time that we add a new partition for, we take the last partition statistics, and after we've gathered those to get them accurate, we copy them over to the next window of time, and we run with those statistics until that partition fills up, and we go to create another, and then we go through that process again. Dynamic sampling is another approach. We saw an example of that. We'll take a look at some SQL profiles, extended statistics, cardinality feedback, and the cardinality hints. So dynamic sampling, we've already demonstrated that. If you want to see more examples and read more about it, you can Google up site www.oracle.com, my last name, dynamic, wrote an article on it. It goes through all the levels of dynamic sampling, exactly what happens and how it works. So level 3 is the one that I used in my example. It will sample during a guess for single column, single table guesses. Level 4 takes it up a level, but can do the multi-column, multi-table sort of guesses. Then there's levels 5 through 10 in versions 11 and before. That just increases the volume of the dynamic sample. And in version 12, dynamic sampling actually goes to 11. And when it's set to level 11, those dynamic samples can not only be used for the query that's being parsed currently, but we can use that information across queries for the first time. And we can also make that information persistent in the form of a SQL plan directive that we'll remember in the data dictionary so that we'll know when we need to dynamically sample query by query. And basically the database will organize those facts for us. SQL profiles. There's a lot of confusion on SQL profiles. I've often heard people refer to a SQL profile as a workaround, as a hack, as something to be avoided. And I disagree with that entirely. A SQL profile is simply a method for you to be able to analyze a query. Just like DBAs analyze tables, DBAs analyze indexes, and they don't think twice about doing that. They know that that's something you need to do. A SQL profile is analyzing a query. When you submit a query to be SQL profiled, the database will look at the execution history. It will also, if time permits, rip that query apart and do a really intense sort of dynamic sample. It will look at the bits and pieces of the where clause and it will say, you know, I estimated I'm going to get 5,000 rows. And it will actually execute that part of the where clause against your tables using various bind variable values to figure out what the true estimated cardinality was. Well, I guessed it was going to be 5,000, but I'm really only seeing 5. And then it will remember that information into the data dictionary. The next time you go to optimize a query that has a SQL profile, as the optimizer is coming up with its estimated cardinalities, it will look at this additional information in the SQL profile to see how to adjust those estimated cardinalities. So you see a SQL profile is just a way to get the optimizer to get the correct cardinality estimate. If we get the right cardinality estimate, we're going to get the right query plan. So SQL profile is not a hack, it's not a workaround, it's not something to be avoided. It's simply like more statistics. Just like a DBA might go in and say, oh, we'll add histograms, and that will come up with better cardinality estimates. We'll add a SQL profile, and that will come up with better cardinality estimates. Now, one thing to remember about a SQL profile is, just like statistics on a table, a SQL profile can go stale over time. So if the size and shape of the data changes radically, just like a DBA would gather stats with DBMS stats, they may have to regenerate a profile in order to get the right cardinality estimates sticking in there. Okay? Here's an example of a SQL profile. It's sort of an odd one because it's not really going to fix the estimated cardinality in the query based on misinformation about the where clause, because there is no where clause. It's going to fix the estimated cardinality based on the historical usage pattern of this query. So in this case, I have a query select some things from a table ordered by some indexed column. So that's on lines 5, 6, and 7. Now the developer, in a database-independent fashion, opens that cursor, fetches the first 10 rows, prints them out, and then closes the cursor. They could have used row number. They could have used fetch first, fetch next in version 12. They could have used row num. They could have put information into the query that would allow the optimizer to know we're only getting 10 records and we're stopping, but they chose not to. So what the optimizer gets to optimize is simply the query select blah from table order by some indexed column. Now, if you had that query to optimize, you would probably look at that and say, using an index to read every single row out of the table, not the fastest way to do it. What I'm going to do is a full scan, a sort order by, potentially writing that data to temp, and then return that back to the application. What the optimizer doesn't know is that the developer is always going to stop after 10 records. They're never going farther than 10 in this particular application. So every time we run this query, it does a full scan and sort order by. We can see how many rows flowed through the full scan, almost 50,000, but then only 10 came out of the sort order by. Okay? The database is recording this information. It's in the $$ tables. It's in the active session history, but the optimizer doesn't see this when it's optimizing the query. So what we'll do is we'll run a SQL profile on that. I'm doing it the manual way. You can just go into Oracle Enterprise Manager, create a SQL tuning set, add this query to the SQL tuning set, and ask for SQL profiles on that. But here's the way to do it manually. I'm finding the SQL ID for that query, and I'm creating a tuning task, and I'm running that tuning task. After that tuning task is run, I can come back and generate a report that would tell me what happened here. And basically it's saying a potentially better execution plan was found for this statement. And this is the original query. We assigned it this cost because we think we're going to have to run through almost 50,000 records, sort them, potentially write them to temp, and then return 50,000 records to the application. But with the SQL profile, we're fixing the estimated cardinality. We think that through that index, we're just going to get 10 records. And by stuffing that number 10 in there, it dramatically lowers the cost of that particular plan. If we just let the cost-based optimizer stick with what it wanted, it's going to think every record in the table. It's going to do the full scan sort order by. But if we override that and tell them, hey, you're going to get about 10 records, they're going to come up with the index range scan. And so here we have a query plan that's going to change based on its execution history. You know, it's not that the optimizer got the estimated cardinalities wrong, because there are 50,000 rows in the table. It's that the cost-based optimizer didn't understand how the application was using that query, didn't know it was just getting the first 10 records. So by giving that information in the form of a SQL profile in this case, the optimizer comes up with the right estimated cardinality. What would be other ways to do this? The best way probably would be to use the fetch first clause in Oracle 12c or row underscore number or row num analytic built-in functions in 11g and b4. In that way, the optimizer will actually see that you want the first 10 records and return them. Alternatively, if you didn't want to use row num or row underscore number for whatever reason, put a first rows in there. You could say first rows, open parentheses, 10, close parentheses. That's going to have a similar effect. That's going to tell the optimizer that we're only going to get 10 records out of here. We're interested in getting the first 10 records as fast as possible. And it's going to drive the optimizer down the same path. But all of these are ways to give the optimizer this additional information. Developer can tell it through the first rows hint. Developer can tell it with the row underscore number, row num, analytics sort of built-in functions in a where clause. Or the DBA can come by after the fact with a SQL profile, gather statistics on the historical execution of that query, and have that information be applied at hard parse time. But the ultimate goal is to get the cost-based optimizer to come up with the right estimated cardinality of 10 in this case. Right cardinality, we get the right query plan. Another approach to fixing the cardinality misestimates is extended statistics. This is the ability to create statistics on a set of columns or on an expression. Like if I had a where clause where column A plus column B divided by 2 is greater than 50, basically says where the average of A and B is greater than 50. The optimizer might have a lot of information on A and a lot of information on B, but it might know nothing about A plus B divided by 2. We can now, in 11G and above, gather statistics on that expression so that when the optimizer sees it in the where clause, the optimizer can come up with a correct cardinality estimate. So here's a quick example of that. We'll create a table as a copy of all objects. We'll have an index on owner, object type, gather statistics on this, gather really good statistics. We'll get histograms on all of the columns in the table just in case. So everything sitting out there, this is the most we can gather with this initial DBMS stats. And we'll come in and we'll run a pretty simple query, select star from the table, where owner equals public and object type equals Java class. Now, we have a similar problem to that flag 1 and flag 2 problem. The database knows how many owners equal public records there are. And there's a lot, right? Because, public has all those public synonyms and everything. The database also knows how many object types are Java classes. Again, that's a lot. Sys owns a lot of Java classes. But what the database optimizer doesn't know is there's a relationship between the owner and the object type. If your owner is public, most everything you own is a public synonym. If your owner name is sys, lots of things you own are Java class, or more specifically, if your object type is Java class, your owner is almost certainly sys in most databases. So there's a relationship between these two columns. The database doesn't know this yet. So the database is going to take the probability of an owner being public, multiply it by the probability of an object type being a Java class, and come up with an estimated cardinality. In this case, 9,000. Now, it's going to do a full table scan for that. The actual answer is 0. There are no records that match this criteria. A full scan was a bad idea. So what we will do is create extended statistics on the columns owner, object type. So instead of gathering stats just on owner and just on object type, it's also going to gather stats on owner, object type simultaneously. So we go ahead and we gather those stats and we rerun that query, and notice the estimated cardinality drops from 9,000 down to 7. 7 is close enough to 0 to get the right query plan. The query plan has in fact changed. Because we got the right cardinality, we get the right query plan. This works with expressions as well. Okay, so we can do these on functions and expressions. And so, for example, I'm going to create a table T with those columns A and B that I was talking about. But notice when I create those two columns, B is always the negative of A. So in fact, A plus B is always going to result in 0. But the optimizer doesn't know that. It just sees the range of values for A, the range of values for B. And if we take a look at this after gathering stats, and we look at a magic number, 5% of the rows in the table, we can see that that number would be 3,635. So just remember that number for a minute. Now the optimizer is going to come along, and we're going to give it a query, select star from T, where A plus B divided by 2 is greater than 50. Again, It knows a lot about A, knows a lot about B, knows a lot about table T, knows a lot about the indexes on it, et cetera, knows nothing about A plus B divided by 2. The optimizer has to guess. What does it do when it guesses? Well, sometimes it multiplies probabilities together, like it did in the last example with owner equals public and object type equals Java class. Sometimes it just has to outright guess. It sees this expression and it says, you know, I'm going to punt on this one. I'm going to guess that it's about 5% of the rows in the table. And in the previous slide, we saw 5% was 3635, and sure enough, it's estimating 3635 as the estimated cardinality. You know and I know, however, because we constructed the data, it's really 0. So what we'll do is we'll go ahead and generate extended statistics on that expression, gather stats from the table, and the next time we go to run that query, the estimated cardinality drops to 1. It knows exactly what values are available for that expression now. And it can come up with a very accurate cardinality estimate. But this just demonstrates again that even though it's 0 is the actual answer, the cost-based optimizer will always estimate at least 1. You'll never see a cardinality estimate of 0 inside of a query plan. But 1 is closer than close enough to 0 to get the right plan. Another one is cardinality feedback. This was introduced in 11G and is actually enhanced in version 12. Here's a popular function that I use frequently, and I know lots of other people do as well. It takes a string as an input and turns that comma delimited, that pipe delimited string into a set. And basically what it allows you to do is select star from the string. Okay? And when I do that, I now have the ability to bind an enlist into my query. So my application could create 1, 2, 3, 4, and it can use one bind variable to bind that in, but then use that in this string to table function to turn it into a set so that I can use it in an enlist. And so this query shows you how to do this. Pretty straightforward, pretty simple. But one of the downsides to this is the cardinality estimate. The optimizer is optimizing a query against that function. That function, we can't gather statistics against it. We have a very hard time associating any sort of statistics with it. So the optimizer has to guess. And in this case, the optimizer is always going to guess 8,168 because I have an 8K block size database. If I want to change that estimate, one approach I could do is rebuild my database with a 4K block size table space as default, and the optimizer would start estimating about 4,000 rows will come out of that function. But that's not a very good way to influence the optimizer in this case. What we'd like to do is have the optimizer be able to come up with the correct cardinality estimate based on what it's seen happen with this query in the past. So I go ahead and I run that query a second time, and that's all I did was I reran it, and the estimated cardinality is now coming back as initially 8,168, but after that step, it says, I only saw 3 rows come out. I made a mistake last time. I had an estimated cardinality that was way off from what I expected. So when I ran that query the first time, I was watching the rows coming through each step in the plan. I was expecting 8,000. I only got 3. So I'm going to fix that the next time you run that query. I'm going to stick the number 3 in there, and we're going to re-optimize that query. So the database becomes a little bit self-adjusting. Ran the query the first time, realized it made a mistake, and fixes the query for subsequent executions. Here's another example with the cardinality feedback, taking it to its full extreme. Create a table T, select star from all objects, index object name, gather stats on that. We'll go ahead and take that in list, right, and I'm going to use it as sort of a filter against table T. So I want to bind in a comma delimited list of the objects I'm interested in and just see those pop out. Now the first time I run that query, it's doing a full scan and a hash join to table T because it thinks it's going to get 8,168 rows out of this temporary table, out of the string to table function. The second time I run that, however, the query plan changes. And we have a note here that cardinality feedback was used in this case. Now, it ran the query the first time, said, hey, I think we're going to get 8,168 rows. but when it ran it in real life, it said, I only got 3. So it stuffs number 3 in there, and that completely changes the rest of the query plan. Instead of doing a full scan and hash join, it flipped to the desired nested loops. Now, it's true that with cardinality feedback, we need to make a mistake the first time. But once we've executed the query once, we readjust the plan, and this is the plan that is now in the shared pool, and this is the plan that we'll use until it ages out. Another opportunity is to use the cardinality hints. The developer, they know about how many rows go out of this function. They wrote the function, they wrote the application, they know it produces about 10 records, right? And so with the cardinality hint, which I don't have yet, we would get without the cardinality hint, we get the full scan. But if I come back and say there's about 10 records that are going to come out of this function, the next time I run the query, instead of getting a full scan and a hash join, the optimizer says, ooh, only going to get 10, and that rewrites the rest of the query plan. So I'm going to be using the index range scan, table access by index row ID, get your information out. In short, the optimizer doesn't really care where it gets the statistics from. It just wants to get cardinality estimates that are nearly accurate. If it can get cardinality estimates that are nearly accurate, it's going to get the right query plan. And we've seen in this presentation some of the tools you have access to. DBMS stats, making sure that the statistics on the object are representative of the object. Gathering additional statistics like histograms. And if we leave the method opt off of our gather stats, we'll find that DBMS stats will actually gather histograms on data with skewed values automatically for us. I demonstrated that when all I did was I gathered stats and my query plan changed because the optimizer came and built a frequency-based histogram the second time we gathered stats after running a query against that from status column. So just letting DBMS stats do its job will get us better statistics. You have extended statistics in 11G. You have SQL profiles in 10G and above. You have dynamic sampling in 9i and above. You have the cardinality hint for when all else fails. So there's many different approaches. And you may be sitting out there thinking this is really a talk for DBAs. I think this is more talk for developers, because these are things developers should be thinking about, because they know their data, they know their application. They should be able to come up with the best approach for getting the right statistics into the optimizer. And what I'd like to finish up with here is when all else fails. I've got a query, getting the wrong estimated cardinality, getting the wrong query plan, can't figure out how to fix it. Or I've got a query and it's getting the right estimated cardinalities, but you know what? If it used this alternative plan that I figured out by hinting the query, it runs much faster. That's a bug in the optimizer. That's something we should file an SR for and get fixed, that second case where it's getting the right cardinality but coming up with the wrong plan. But those cases are very rare. But you may have a query where everything seems perfect and it's still getting the wrong plan, and you find if you hint it, you can get a query plan that runs much better. We, in general, do not want to hint queries and have those hinted queries go into production. They introduce a maintenance issue. As I go from version to version, a set of hints that ran in one version and produced the right query plan may not produce that same query plan after I upgrade. And in fact, a set of hints that appears to work, you know, I threw a useNL hint into a query and it's now using a nested loops join, may not work just after a gather statistics happens. I don't even have to upgrade the database, because useNL, the use nested loops hint, only makes sense if I'm going from table T1 to table T2. If the optimizer says, hey, I'm not going to drive from T1 into T2, I'm going to go from T2 into T1 because the estimated cardinalities tell me to go that way, that useNL hint may not be utilized simply because the ordering of the tables has changed. You didn't know that when you use the useNL hint, you should also always use the ordered hint and many other hints. You have to really be explicit with guarantee that you're always going to get the same query plan over and over again. So using hints can be dangerous. However, if you can, in a production or test environment, hint a query and get the plan you want, then we can in fact tell the database to use that particular query plan. And this is a feature that's part of SQL plan management, SQL plan baseline, something that was introduced in Oracle 10 and greatly enhanced in 11G. Basically, if you can hint a query, if you can get into SQL Plus and have that query run with a plan you want, either by changing a session environment variable in the init.aura parameter, faking statistics on the table, putting a hint in there, if you can get the right plan for that query, we can take that plan for the hinted query, for the query in the session with different settings, and tell the database to use that query plan for this query, even without the hints, even without those session settings. So basically, if you can hint it, we can baseline it. And this will make it so that you never need to put into production a query with hints inside of it. And this is the approach you would take. First, let me explain SQL plan management. Basically, an application submits a query to the database. The query gets parsed and generates a plan. If you're using SQL plan management, before that plan is used, the database will look in the plan history and see if there's a query plan for that query. If there is, it will verify that the plan it generated is one of the accepted plans for that query in the baseline. If there was a query plan in the baseline and it was accepted and it did not match the one we had generated, we wouldn't run that query we had just generated. We'd use the one from the baseline. So the baseline accepted plans override the generated plans by the optimizer. So we come in, submit the query, it generates the plan in blue. The plan in blue is in the plan baseline, so that plan's acceptable, and we'll go ahead and run with it. On the other hand, you may have a situation where you come in, submit the query, we generate a brand new query plan, never existed before. That plan is not in the baseline for that particular SQL statement. So in the baseline, there is a plan for that SQL statement. It doesn't match the plan in red. We're not going to run the plan in red. We're going to put it in the plan history, and then we're going to pick up the plan from the baseline and continue to use that. Remember my example way back at the beginning where I added one row to a table, and when the estimated cardinality went from 292 to 293, the query plan went from an index to a full scan? SQL plan management just used out of the box, so forget hints for a minute here. Just SQL plan management used out of the box can help make that safer. If I was using SQL plan management, okay, on day one, the cost-based optimizer estimated 292 rows, came up with the plan in blue, said index range scan, that's in the baseline. Great, run with that. Somebody gathered statistics. The next day, we come up with a query plan that says, I think 293 rows, I'm going to do a full scan. Well, nobody's ever tested the full scan yet. It's not in the baseline. We haven't run that query plan. Rather than run it right away, SQL plan management will file that into the plan history, and it will continue to use the index range scan. Okay, so the plan won't change right away. We have generated the new full scan plan, but we're not going to use it. With SQL plan management, either an automated task that runs in your maintenance window or the DBA can run this task, would take all the red plans, the ones that are in the plan history that haven't been tested yet, and it would actually run those plans against your data and verify that the new plan runs significantly better than the old plan. So we generated that full scan plan. Right? We decided not to use it. We put it in the plan history. We continued using the index range scan. Later that night, a database maintenance job can pick up that red plan, the full scan. It'll run it. And if that runs faster than the index range scan, it would then change the color of that plan from red to blue. It would accept that plan. It would enable that plan. And we could start using the full scan plan from that point on. If, on the other hand, adding that one record to the table wasn't sufficient to make us go from an index to a full scan. If the full scan ran just as fast as the index range scan or maybe even slower, SQL plan management would mark that red plan as a bad idea, leave it in the plan history. We wouldn't use it. We'd continue using the index. In a few weeks, that red plan would age out of the baseline. The optimizer would be free to come up with a full scan again. However, it would get stored in the plan history. We'd continue to use the index range scan until we tested the full scan once again. And maybe 2 or 3 months from now, the full scan plan makes sense, and we'd start using it. So SQL plan management gives you a way to get query plan stability. I know what plan is going to be used for an individual query, but it also allows us to get new plans to be generated. And if they turn out to test faster than the old plans, we have the ability to use them. So let's get back to the, if you can hint it, you can baseline it. I'm going to show you an example of a query where it's going to start with 2 full scans and a hash join out to a group by. But we've discovered through our internal testing that if it was actually to use an index range scan on the products table and then a full scan and a hash join to sales, everything would be good, much better. That's the plan we would like to use. However, we can't change the query in the application, can't rewrite it to have a hint. Maybe it's a third-party application. Maybe it takes 2 weeks to get a change like that out into our production environment. Or we've just heard that hinting queries in production code is a bad idea, which in general it is, and we'd like to avoid that. Here's the steps you would go through. The first thing you would do is execute the bad query. So we go ahead and execute our query. This gets us our full scan hash join. So this is the undesirable plan. And the first thing we'll do is we'll load that plan into the SQL plan baseline. So we need to get the SQL ID for that. We get the SQL ID out of $SQL, and then we load that plan from the cursor cache. And so now it's in the baseline. What we have in the baseline is the plan we're not going to want to use in the future. So what we'll want to do is, after that plan's been loaded in the baseline, is disable that plan and say, this is not a desirable plan. So right now, if you envision what's happened is, in the plan baseline, we just have the one query plan, which is the 2 full scans hash joins. It's not enabled, but it's the only plan that's sitting in the baseline. So now, when the optimizer comes in and optimizes that original query, it will come up with the 2 full scans and hash join. It will look in the baseline. It will discover that there's no accepted plans in the baseline, so it will just run the 2 full scans and hash join that it has. So far, nothing's changed. But we have created a plan baseline. That plan baseline has a SQL handle, which is sort of an identifier for that, so you can see the SQL handle down there. And it's for that SQL statement that we ran just 2 screens ago. So what we'll do now is run our query in an environment where it gets the plan we want. I could have done an alter session. I could have changed an init.or parameter. I could have gathered private statistics. I could have set private statistics. In this case, I'm using an index hint and saying, I'd like you to use an index on the products table. So we'll go ahead and run that. We can now see in $SQL that that SQL statement is there. We have the SQL ID for it. We also have the plan hash value. So a given SQL ID could have multiple plans associated with it. We're picking out a unique key for that SQL ID and a query plan. This is exactly the plan we'd like to use. We now load that plan from the cursor cache. But notice we're taking that SQL ID and plan hash value from the previous screen, and we're taking the SQL handle from a couple of screens ago. This is the SQL handle for the baseline for our poorly performing query. And what we're doing is taking the plan for our hinted query, which is right here, and we're loading it into the baseline for our poorly performing query. If we look in that baseline, there will now be 2 plans in there. One is enabled, one is not. The one that is enabled is the plan we just loaded in there, but notice the SQL text that's associated with it. It's not the hinted SQL text, it's the original SQL text, because we took this plan for this query and loaded it into the baseline for a completely different query. Now, the plan we loaded in there is valid for this completely different query. because the only thing different between them is a hint or so in the query itself, or a session parameter value or something like that. So we now have an accepted plan in the baseline. That accepted plan is the plan for our hinted query. The next time we go and run the unhinted query, so we don't have any hints in this, we can see it's using the plan hash value from the previous screen, from the query plan we just loaded in there. It has our index range scan as well as the full scan in the hash join, so we can see we got the plan we desired. And down at the bottom of this output, we have a note that says the SQL plan baseline was in fact used for this. So this allows you to basically fix a query plan in your running production system without touching the query in the running production system. Just get into an environment, your test environment, your QA environment, get the plan you want, and you can actually export that, import that across databases, or if you're doing the work in a single database as I was here, you can get that plan loaded into the baseline, and for that query, you've patched it. Now, what if the other query plan at some point starts to become the better query plan? We'll still have an opportunity in the future to reevaluate this, to take a look at all these query plans, test them in the background, run them against your data, and if the other query plan eventually becomes better than the one we've just put in there, you'd have the ability to accept that plan as well. So with the SQL plan management, you have the ability to fix a query, right? Get the query plan you think you want in there, but if a better query plan comes along in the future, we can start using that better query plan with the SQL plan evolution. If you were to hint the query, that query plan hopefully would never ever change. I mean, that's your ultimate goal there, but you might want that query plan to change at some point in the future. This will allow you to have your cake and eat it too, in a sense, because you'll be able to fix that query plan, but also allow that query plan to evolve over time. Okay. It's exactly 2 o'clock, and I'm sort of out of time at this point. So I'd like to thank you very much for your time and attention. Hope you found it useful. If you have any serious follow-up questions, I'll make sure that these slides are available. I'll upload them to asktom.oracle.com in a couple minutes, so you can download them, get all the links and examples and stuff. But if you have a burning question that wasn't answered, feel free to email me at thomas.kite@oracle.com, and time permitting, I'll get back to as many people as I can. But otherwise, thanks very much for your time and attention. And again, hope you found it useful, and hope to see you at ODTUG this summer in June. I'll be up there in Seattle doing quite a few sessions.